Hello, warm welcome to everyone joining. Thank you for being here. Get yourself ready. Grab a notebook. You can get a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a little bit of Trig meets Algebra review. This is intended to get you set up for what you'll need and what you should have learned from Precalculus, but to bring back some of the tougher problems so that as you step into calculus, you'll be well equipped, your tools will be sharpened. Go ahead and give this problem a look. You can see that it's got some trig equalities to it, and it's got some algebraic qualities to it. It is an equation after all, and we have a squared. So I'd like to give you maybe about 5 minutes to try this problem on your own first. Give it a shot. And then when you're ready, you can come on back and see what trig identity or trig properties you might have forgotten about, what you might have missed. You can unpause the video and continue this to see how we do it here. Great. So to get started, we're going to use an identity. The mother identity, sine squared plus cosine squared is equals to 1. The way that's going to help us is that if we were to subtract cosine squared, that would leave us with an expression for just sine squared, which is going to allow us to replace sine squared with something that is involving cosines instead. And that's going to be useful because you'll notice that there's another cosine term in the equation. Right? We can't solve this equation as it is with a sine in it and a cosine in it. It's too difficult. So we're going to make that replacement. A very simple replacement to start off with. And if you didn't remember that identity, you should take the time to remember this mother identity. There are two other Pythagorean identities. This is the main one that you should be familiar with, although there are two others. They're important too. They matter. So when you get a chance, make sure you go over those identities. Let's continue with the problem. We're going to distribute the 2. And when we do that, we get a nicer equation. Now everything is with a cosine of theta. That's the only trig expression that's here. And we also get this nice property on both sides, where they're equal to 2. So we can subtract 2 from both sides. And that really simplifies our equation quite a bit. Now this is where the algebraic structure comes in. Because this is of the same format as a quadratic, something that looks like this, negative 2x squared plus square root of 3x equals 0. That's basically what we have here. But instead of x, we have cosine theta. Right? So we have cosine theta as our x, and the x squared is the cosine squared. So let's move this around a little bit. We could just use a common factor to pull out cosine theta, and we'll be left with negative 2 cos theta plus square root of 3. Right? If I factor a cosine out of cosine squared, there's still a cosine left. And if I take the cosine from you, I've just robbed the cosine, there's no more cosine. And we get to use the beautiful zero product property. It's so useful to use the zero product property. It basically says that when two things are being multiplied, so that's this cosine theta and this entire packet in the parentheses, negative 2 cos theta plus 3, when those two are being multiplied, if the result is 0, that means one of them had to be 0. So that means either cos theta equals 0 or this expression equals 0, which could be moved around a little bit. We can manipulate things a little. And it would say that root 3 equals 2 cos theta, which means root 3 over 2 equals cos theta. So we can work with that. We've gotten this down from an algebraic sense, and now it's up to the trigonometry knowledge that you have to take you the rest of the way. Whenever we have an equation that says sine theta equals, or cos theta equals, or tan theta equals, we need to use the sine inverse or cosine inverse or tan inverse rule. And that rule says that when cos theta equals 0, our theta could be the inverse of 0, which is pi over 2 plus 2 pi k, or theta can be negative pi over 2 plus 2 pi k. The 2 pi k comes from the fact that cosine repeats its values after we've added 2 pi to the angle. But we need to consider these values for k. So let's start off with k equals 0. If k equals 0, then our theta is just pi over 2, and our theta here this would be negative pi over 2. But you need to check something carefully when you're solving trig equations. You might be given a domain or an interval, which we were. We're given this strict interval from pi to 5 pi over 2. So our theta values need to be at least pi, and the greatest they can be is 5 pi over 2. So let's see what that would give us. Well, these are not in range, so neither of them are accepted. We reject those answers. If k equals 1, let's try to find new theta values. We'll have 5 pi over 2 and 3 pi over 2. And guess what? Those are perfectly fine. 5 pi over 2 is right on the cusp, but we're allowed to use 5 pi over 2. And then let's see what happens if k equals 2. If k equals 2, that's going to give me 7 pi over 2. Is that right? No, it is 9 pi over 2. We'll have 9 pi over 2, which is going to get rejected. And we're also going to have, 7 pi over 2, which would also get rejected. So none of these are coming with us except for 5 pi over 2 and 3 pi over 2. On the other hand, we have another small trigonometric equation here with more solutions for theta that came from the zero product property. And again, we need to use this cos inverse rule. So theta could be the cos inverse of rad 3 over 2, which is pi on 6 plus 2 pi k. But it could also be negative pi on 6 plus 2 pi k. So I have to go through different values of k until I'm within range. If we start off with k equals 0, pi over 6, you're not going to cut it. Negative pi over 6, you're also not going to cut it. Those are rejected answers. Let's try k equals 1. Then things start to get a little more interesting. When k equals 1, then we would be at 13 pi over 6 and 11 pi over 6. These are both accepted. These are both valid. How do I know these are valid for sure? Well, I need my theta to be between pi and 5 pi over 2. So the question is 11 pi over 6 within that range? If I put these in terms of pi over 6, this would be 6 pi over 6. And this would be 15 pi over 6. So anything within that range is accepted. That means that these two are both good to go, because they're between 6 pi over 6 and 15 pi over 6. Now if we go to k equals 2, then we exceed this range, because that would give us, 25 pi over 6 and 23 pi over 6. These are both beyond the range of 15 pi over 6. So my final answers here are simply 5 pi over 2. Let's maybe put them in order from lowest to greatest. We have 3 pi over 2. And then in between we have 11 pi over 6 and 5 pi over 6. Okay, those are our 4 angles which solve the original equation. And you can go back and check these answers and you'll see that they satisfy the equation. Meaning you can do 2 times sine of 3 pi over 2 squared plus rad 3 times cosine of 3 pi over 2, and this will equal 2. That will work no matter which one of these angles you want to plug in for your theta. Okay, I think this shows exactly what kinds of skills you'll need to look out for when you're solving equations. Remember that calculus is difficult because the small intermediate steps of calculus are the questions you would have solved in precalculus. And you need to be sharp and quick with your precalculus because we're not going to wait for you once we're in calculus. We're going to expect you to catch up if you're behind. All right, I think that's enough blab out of me. See you guys next time.